All right. Hello, everyone. Today is April 6th, Tuesday. It's Tuesday late evening, and I'm sitting down in the office to take lecture videos one by one. Hope you guys had a great weekend and enjoyed the nice weather yesterday. And my aim this week is to cover Chapter 7 in the textbook, Rules of Differentiation and their use in comparative statics. So in the previous week, I introduced the comparative static. That is essentially to address how the state of equilibrium responds to a change in exogenous parameters. And I related this problem to the problem of finding the rate of change. So in case of qualitative question, we examine the sign of the derivative. And in case of quantitative question, we compute the size or the magnitude of the rate of change. And after that, I introduced the derivative. That is our primary mathematical tool for comparative static as the instantaneous rate of change. So the formal definition of the derivative is right here. So whenever we have a function y equals f of x that is differentiable, then the derivative is denoted by f prime or dy over dx. So infinitesimal change in variable y over infinitesimal change in variable of x. Okay. So the ratio of these two infinitesimal changes can be seen as the instantaneous rate of change. And another way to define the derivative is using mathematical limit. So we take the limit of the function's rate of change over the interval between x and x plus h, and then we take the limit as increment of x, so h goes to 0. Okay. So in order to better understand this definition, let me show you one picture that is right here. So we have a y equals f of x, and the blue curve indicates the graph of the function. And we choose two random points on the graph. So one point is x comma f of x. So we evaluate the function at point x. And then the right hand point of the interval x plus h. And we evaluate the function at x plus h to obtain x plus h. Right, so now we examine the movement of the function over this interval. So it corresponds to the case when we increase the value of x by h. So the left hand point of the interval is x. The right hand point of the interval is x plus h. Yeah? So over this interval, we can see that the function changes from f of x to f of x plus h. So the increment of y amounts to the difference between these two, f of x plus h and f of x. So we put this expression on the top in the expression of the rate of change. So because the rate of change is the change in y over change in x. Yeah? And then we put the h on the bottom. So the increment of x. Yeah? So this expression is the rate of change indicates that the slope of this sequence connecting the 2 points at the left hand point and at the right hand point. Okay. Then the derivative, once again, the derivative is instantaneous rate of change. Okay. So now we move this right hand point and toward the left hand point. So now we reduce the size of the interval that is originally given by h, and we examine the slope of the sequence as h goes to 0. So at the first trial, let me reduce the size of the interval to h over 2, and the right hand point now moves to the left to x plus h over 2. Yeah? So now it's heading toward the left hand point. And the associated sequence is going to be this green line. Okay? So now you can easily see that as h goes to 0, it means as the right hand point moves toward the left hand point, the sequence line collapses down to the tangent. Okay? This is why the derivative at point x indicates the slope of the tangent, and this is why the derivative is the instantaneous rate of change. Okay? That is the geometric interpretation of the derivative, and that is very important in understanding our comparative static analysis in the future, and we study optimization theory. Okay? So remember, derivative is slope of the tangent at point x. All right, uh, so in the previous week, we used this definition to compute the derivative of simple functions. But nobody uses definition for computation of the derivative. As a matter of fact, there are several convenient rules that help us to find the derivative in a simple and easy way. So in chapter 7, we are going to study several differentiation rules. And chapter 7, we'll restrict ourselves to the problem of finding derivatives. So chapter 7 is all about the derivatives, okay? So let me start with a constant rule. So when f of x is given by a constant function c, and its derivative is going to be 0, that is quite intuitive because a constant function's graph is going to be horizontal line on the xy coordinate system. So meaning that the y does not respond at all to change in x. Okay? So it's fixed by some constant c. So in the expression of rate of change, we put the amount of change in y on the top. So we can easily see that the numerator is going to be 0 because this function, in case of a constant function, the function spits out the same value of c no matter what the argument is. So f of x plus h, that is c, and f of x, that is also c. So from the definition of the derivative, it's defined as the limit of this rate of change. So even before taking the limit, we can see that quantity is equal to 0, meaning that the derivative is equal to 0. Right? So whenever we have a constant, and then we take the derivative, that we can see that it goes away. Okay? And the second rule is the so-called power rule. It tells us how to take the derivative of this type of function. So x to the power n. We have a variable x as the base of the function, and the power is given by some constant n. So here, let me highlight this constant n can be any natural number or any negative numbers, negative integers, or it can be rational number or irrational number. Regardless, as long as the n is a constant, we can apply this power rule to find the derivative. Okay? So whenever f of x is given by x to the power n, the way to find the derivative is we first bring out the power, okay, and put it in front. And then we take 1 away from the power. So the new power becomes n minus 1. Right? So that is the derivative. So for example, if we have a f of x, x cubed, and its derivative is power 3 comes up front, then we take 1 away from the power, so the derivative becomes 3x cubed. Okay? And I'm not going to prove this rule, because that is a little bit tedious. So if you wonder the exact procedure of getting this rule, you may refer to the textbook. But I'm gonna show you the proof of this example. Okay? So how do you get 3x cubed using definition of the derivative? So let me open my note. All right, so we have a function f of x given by x cubed. Now I'm looking for f prime. That is a limit of rate of change as h goes to 0. Okay? And because f is given by x cubed, f of x plus h cubed, and f of x cubed. Okay? And now I'm going to expand this binomial expression. So we know x plus h cubed, if we expand that binomial, we obtain x cubed plus 3x squared h and 3xh squared plus h cubed. Okay? Then we take away x cubed, then divide it by h. Okay? So I can see this x cubed will be cancelled off by the last term because we have 2x cubed. So they will be cancelled off. And the remaining terms have at least one h. Okay? So by dividing by h, I just reduce the power of h by 1. So first term is going to be 3x squared, and the second 3xh, and the last one h squared. Okay? So I can see that these two terms will go away as h goes to 0. Right? So I'm left with just a 3x squared. That is the derivative of x cubed. All right, so in case of number n, now the thing is how to expand. So how to get the expression of the expanding the binomial expression x plus h to the power n. It turns out that there is a nice formula regarding this. So the expansion of this binomial expression x plus h to the power n is the summation of these terms. So n choose k, x to the power n minus k times h to the power k. Okay? But I'm not sure how many students are familiar with this notation. N choose k is called a combination. Its formula is n factorial divided by k factorial times n minus k factorial. So it is used to count all possible cases in probability theory or statistics. But we never use this theorem except a proof of power, so let me skip this. Okay? So using this binomial theorem, you can formally prove that f of x's derivative is n times x to the power n minus 1, but that is not that useful. More useful thing is how to apply this rule to some economic problems. So we are going to put more focus on that kind of application. And the third rule tells us whenever scalar multiple, so whenever we have a function as a scalar multiple c of f of x, and the derivative is, we can pull out the constant. So the derivative is c times f prime of x. So constant c, whenever that is multiplied, it can be pulled out. Okay? So the way to prove this is we call that inside the function g of x. Okay? And the left-hand side is g prime of x. And now using definition, we can compute the derivative of g. So because the g prime is the limit of the rate of change of g, so a g function is defined as c times f of x plus h, and c f of x, and divided by h. Okay? Because we define function g as c times f of x. So g of x plus h becomes c times f of x plus h, and g of x, the original definition, we substitute. All right, then I can see the common factor c, so I can factor out c. So to rewrite this as c times limit of f of x plus h minus f of x divided by h as h goes to 0. So after rewriting the derivative of g, now I can see that this limit is nothing but the derivative of, okay? So we conclude g prime is c times f prime. All right. And for the remaining rules, I will show you without the proof. Okay? So the first rule is about the sum and difference. So the derivative of the sum is going to be the sum of the derivatives, and the derivative of a difference is going to be difference between the derivatives. Right? So armed with these basic rules, now we can differentiate all polynomials or and hyperbolas. And so let me show you several examples of how to apply the previous rules to find the derivative of several polynomials and even hyperbolas. So let me do first example. So y is given by negative 7x to the power 6th. Okay? So y is given by negative 7 x to the power 6th. So if I call this function f of x, then y prime and f prime of x, or dy over dx, or df over dx, all of these four symbols indicate the derivative. Okay? So we use prime notation to represent the derivative, or the ratio of two infinitesimal changes to represent the derivative. So now we compute the derivative of this using the previous rules. So negative 7 is multiplied, so we leave it alone. Negative 7, so y prime is negative 7. Now we multiply by the derivative of x to the power 6th, and using the power rule, we know that the derivative is the power 6 comes out front, and we take 1 away from the power, so the new power becomes 5. So the derivative is negative 42 x to the power 5. Okay? And let me do one more example. The second, that is a difference between several functions, but we know by the fourth rule, the derivative of the difference is going to be difference between derivatives. So using this, we can just take each term in this expression to find the derivative. Okay? So y prime is the derivative of the first 13 that is multiplied, so leave it alone. And then x to the power 4th, its derivative is 4x cubed. Okay? And for the second, negative 6, that is multiplied, so leave it alone. And then x cubed, the derivative is 3x cubed. Okay? And negative x, its derivative is negative 1. And finally, negative 1 is a constant. So by the constant rule, its derivative is going to be 0. So derivative of y with respect to x is going to be 52 x cubed minus 18 x squared. All right. And let me leave the third example for exercise. And instead, let me do the last one. So now y is given by x to the power 1/4 minus 2 over x. Okay? And before taking the derivative, let me use the fact that reciprocal becomes a negative power. So remember 1 over x equals x to the power negative 1. So using this fact to rewrite the function into y equals x to the power 1/4 minus 2 times x to the power negative 1. Okay? Because a 2 over x is 2 times 1 over x. Okay? Now, instead of reciprocal, I can put in the x to the power negative 1. Okay? So y prime. Now, using the difference rule and the power rule, I can find the derivative of y with respect to x. So x to the power 1/4 is going to be 1/4 x to the power. Now we take 1 away from the power. So the new power becomes -3/4. And -2, that is multiplied. So leave it alone the constant. And x to the power -1 becomes, we bring out the power and take 1 away from the power. Okay? So the derivative is 1/4 x to the power -3/4 plus 2 x to the power negative. So that is the derivative of the last example. All right, and in the next exercise, we are asked to find the equation of the tangent to the curve. Now the curve is given by some cubic equation at some given point t. Okay? And remember that derivative delivers information about the slope of the tangent. Okay? And we know the line of the equation. So uh, if the line segment has the slope m and passes through the point a comma b, its equation is going to be y equals m times x minus a plus b. Okay? So the slope of the line is going to be m, and it passes through a comma b. Okay? So if we have some curve, y equals f of x, now we are looking for the equation of the tangent line at point 2. Okay? So we need two pieces of information. First, the slope that comes from the derivative, and the coordinate of the one point. And that will be on the graph. So we are looking for the tangent at point 2. So let me first find the coordinate of this point by just evaluating this function at point 2. So at 2, this function takes the value of 6 minus 2 cubed, that is -2. Okay? So I can see that the graph of this function and the corresponding tangent at point 2 will pass through 2 comma negative. Okay? So A is 2 and B is negative. Okay? Now the remaining thing is the slope. So we take the derivative of this curve to get y prime as 3 minus 3x squared. Okay? So it tells us the slope of the tangent line at any point of x, but we are interested in the slope of the tangent line at point 2. So we substitute 2 for x to get 3 minus 12, that is -9. So m turns out to be -9. So now we are ready to construct the equation. -9 x minus 2 minus 2. So -9x plus 18 minus 2. So 9x plus 16. Okay. All right, and the fifth rule is about the product. So how to take the derivative of a product between two functions. So f and g are multiplied, and we are looking for the derivative. And the way to find the derivative is we first take the derivative of the first function, okay, so f prime, and then we multiply by the second function. Okay? So we leave the second function alone and just multiply by the derivative of the first. Now we interchange the order. So leave the first function alone, f of x, and then multiply by the derivative of the second. Okay? So f times g's derivative is f prime times g plus f times g. So using this product rule, we can find the derivative of these type of functions. So in each example, we can see that two functions of variable, the same variable are multiplied. And so for instance, in the second example, we have a one function of t that is multiplied by another function. Okay? So how to find the derivative of g? So let me first rewrite first function, cubic root of t squared. And remember, cubic root of t is equal to t to the power 1/3. So in general, nth root of t becomes t to the power 1 over n. So square root of t is equal to t to the power 1/2, fourth root of t, t to the power 1/4, and so on. Yeah, but here we have a t squared instead of t. That's going to be t squared to the power 1/3. And by the law of exponents, we just multiply these two powers to get t to the power 2/3. Okay, so the first function can be rewritten as t to the power 2/3, and that is multiplied by one polynomial. So g prime of t. So using the product rule, and we first take the derivative of the first function. So 2/3 t to the power negative 1/3. Using the power, now it is given by the one rational function, but does not matter. And we can bring out the power and put it in front and take one away from the power. So the new power becomes negative. Okay? And then multiply by the second. So leave the second function alone. And then plus. Now we interchange the order. So leave the first function alone and multiply by the derivative of the second. So 2t becomes 2 and t squared becomes negative 2. Okay? So that is the derivative of this, the product of these two functions, right? Yeah. So I leave these two exercises. So I leave the left. So I leave the two remaining examples for exercise. So I believe you guys can find the derivative using this product rule by yourself, right? And using this product rule, we can find the one important observation. So we can make one important observation in producer theory. So, in fact, there is a very important relation between marginal revenue function, so increment of revenue from selling one unit, and the price elasticity of demand. But let me postpone to the live lecture this Friday. So I'm going to explain this application of the product rule at the live lecture this Friday. Okay? Now let me move on to the quotient rule, the last rule in this video. So whenever we have two functions divided by each other, so f of x divided by g of x, and the way to find the derivative of division is the following. So we first raise the power of the bottom to 2. So g of x becomes g of x squared, and the numerator becomes, we first take the derivative of the top, and then multiply by the bottom. And then take away this quantity, so the function on the top, and then multiply by derivative of the bottom. Okay? That's the way to find the derivative of division between two functions. So this rule is applicable only when g of x is a non-zero number. So remember, whenever we encounter this type of function, we should be careful. We should make sure that the denominator is a non-zero number. So the rule is applicable only when g of x is a non-zero number. In other words, this is true at every point x where f divided by g is well defined. right? So now using this rule, let me find the derivative of the first two examples. Okay, so in the first example, we have a 6x squared on the top, and then 2 minus x on the bottom. So we divide 6x squared, one function of x, by another function 2 minus x. Okay? So using this quotient rule, we can easily find the derivative of this. So in separate note, let me explain how to find the derivative of this. So y is given by 6x squared, 2 minus x. Okay. So let me call the top f of x and the bottom g of x. And y prime is, so first, according to the quotient rule, the bottom becomes the original function squared. So the bottom in this example becomes 2 minus x squared. Okay? And on the top, we first write the derivative of the top. So the derivative of f of x, that is 12x. Okay? And then we multiply by g of x, so the bottom, 2 minus x. And take away, we subtract away this quantity. So now the top f of x, so 6x squared. And then multiply by the derivative of the bottom. 2 minus x derivative, that is negative 1. Goes constant 2 by the constant rule goes away, and negative x becomes negative. Right? Then I can simplify the numerator by distributing 12x. Okay? And we have two negative signs here, so we'll be back up to be the positive. So 24x minus 6x squared over minus x squared. Okay? It is the derivative of the first example. And let me do one more example. The next one. Now the function h is given by 3y plus y to the power fourth. So one function of y divided by 2y squared plus 1. So divided by another function of y. Okay? So h prime is, so let me first write down the bottom. So 2y squared plus 1 squared. Okay? And going back to the, okay. So on the top, we first take the derivative of the top. So 3y becomes 3. And y to the power fourth becomes 4y cubed. Okay? And then multiply by the bottom. So 2y squared plus 1. Okay? Now we change the order, right? So according to the quotient rule, the first term is derivative of the top and multiplied by the bottom. Now we change the order. So we leave the top alone and multiply by the derivative of the bottom. That is the way to remember this one. Huh? So now we subtract away f of x. So 3y plus y to the power fourth and multiply by the derivative of the bottom, that is a 4 times y. Right? 2y squared becomes 4y, and 1 constant that is added, so goes away. So I don't think we have to simplify this. Okay? So let me leave this alone. And so that is the derivative of function h. Right? Then I leave the last example for exercise. And there is another application to economics. So quotient rule can be can be established can be used to establish one important relation between average cost function and marginal cost function. So if you took principle of microeconomics, you may have learned this fact that marginal cost curve always pass through the lowest point of average cost function. And using the quotient rule, we can formally prove this. But I'm gonna do this at the live lecture with the previous application, right? Together with the previous application. So in this video, we studied several differentiation rules, starting from the constant rule. So let me go over, because this video is really important uh, we are going to use these rules over and over. Okay? So constant derivative is 0, and power rule, x to the power n's derivative is n times x to the power n minus 1. And whenever scalar is multiplied, we can pull it out. And the sum, or the derivative of the sum, is going to be the sum of the derivatives. And the derivative of a difference is the difference between derivatives. And the product rule, the derivative is derivative of the first times the second. Now we interchange the order. So the first function times the derivative of the second. Okay? And the quotient rule, finally, we first raise the power over the bottom, the 2. So g of x squared. And the numerator is derivative of the top multiplied by derivative of the multiplied by the bottom. And then we interchange the order. So f of x times g prime x. Yeah? But the only difference comparing with the product rule. Now for the product, we added these two expressions. For the quotient rule, we subtract away the second from the first. Yeah? So defined as the difference between these two quantities. Hope you guys enjoyed this video, and I will keep recording lecture videos, so I will see you guys in the next.